Okay guys, we're going to start talking about waves here. So with waves, alright, we'll start just describing them. First thing we have here is pulses and traveling waves. If we take the wave demonstrator like I showed you in class, okay, and I created a pulse there, right? That's just a single oscillation, but if I kept making oscillations, alright, kind of like how I did with that long spring, I'm going to create a traveling wave, or a wave that's going to move down through the medium, okay? So this traveling wave, okay, this is what I get if I kept shaking it back and forth. If I kept shaking it back and forth and then there's that interference, we get that other wave, the standing wave. We're not going to talk about that quite yet, all right? So with this pulse, which is a single oscillation, and the traveling wave, which is multiple oscillations, all right? Both of these, all right, what they end up doing is they transfer energy with no transfer, with no net transfer, I should say, of the medium. So what's happening here, this medium, okay, is the substance through which the wave travels. Right, and we have a couple different types of waves. We have mechanical waves and electromagnetic waves. Those are two ways that we can compare. Mechanical wave requires a medium to transfer energy, okay? An electromagnetic wave, does not require a medium to transfer. An electromagnetic wave is light. We're going to talk about that in a little bit. But really quickly, with mechanical waves, okay, something to know about these guys is that the energy transferred is directly proportional to the amplitude squared. But with an electromagnetic wave, the energy transfer is directly proportional to the frequency. All right, it's an interesting little point right there. All right. Okay, let's go back to this slide here. So a longitudinal wave. This is a longitudinal wave right here. This is a wave in which the direction of the particle's oscillation, all right, is parallel to the direction of the energy transfer. This is like if you took a slinky and compressed it and then released it, all right, it's going to have a nice little effect where it's just going to move up and down the slinky, all right, without that perpendicular displacement. In other words, when we had the wave demonstrator, all right, we were creating transverse waves. All right, the bars were moving up and down while the wave was moving forward. Okay, so that's what we were able to have happen there. All right, so we have a wave diagram here. Really quickly, just to point out, sound is a mechanical wave. Light is an electromagnetic wave. Okay, only light can be polarized, and both can travel through air. Just a quick little point. We're going to talk about what polarization is in a little bit. All right, both can propagate through a gas. Excuse me. Let's just answer that question there. All right. So yeah. Now, really quickly though, when you compare a longitudinal and transverse wave in that way, okay, only a transverse wave can be polarized as well. Okay, and only a compressional wave that's mechanical can go through a gas. If you're looking at a mechanical wave that's transverse, it will not be able to go through a gas. Okay, so transverse mechanical waves cannot propagate. Propagate means move forward. All right, through to the, there we go, it's an A. wavelengths. Okay, so just some quick points to be made there. All right, so let's take a look at a wave diagram. Look at the displacement of the particles with the distance along the wave. Okay. This is displacements. So some quick things to point out here. The anatomy of a wave, all right? The distance between here and here is what we will call the wavelength, right? This distance right here, this is the amplitude, all right? So that's the wavelength. We have the amplitude. So here we have the crest of the wave, the highest point, all right? Here we have the trough. Similar to that, all right, but a little bit, different because it's with the compressional waves here. We have a compression and rarefaction, okay? So compression is an area of high pressure, and rarefaction is an area of low pressure. So high pressure, low pressure here, all right? So our wave diagram, this is if we're looking at displacement versus distance, okay? Another thing that we can consider is going to be displacement versus time of a single particle. If we look at that, okay, what we end up with here, this distance between here and here, pardon me, this segment, this interval, this is the period, and again, this is the amplitude, x naught, looking at the period here. So both of these tell two different stories, all right, about our wave as it moves through space. So the wavelength is the distance over which it starts to repeat, okay, and the period is the time over which this wave begins to repeat, all right? So looking at our little particle here, okay, the motion of the particle is simple harmonic motion, okay? Any particle on a string as it's moving up and down will exhibit simple harmonic motion as a wave moves through that string. Okay, the motion of the energy transfer here in this case, all right, motion of energy transfer is perpendicular to the particle's motion. Okay? In other words, perpendicular to the speed of the wave. So if we look at this motion, all right, of the particle, we can derive the wave equation, okay? So this will be the wave equation we're going to look at here. The first part of this, all right, for the particle speed, okay? So the wave equation is going to come out over here. So for the particle speed, let's just take a look at that really quickly. Particle speed again. Since it's simple harmonic motion, all right, we can average the speed and just take the total distance over which it moves divided by the time. And if we consider one period, okay, delta t is equal to 1 period. Let's come back to the graph and look at the motion of this particle, okay? We're going to see that if we start here, this particle is going to have moved up, and coming back over here, it's going to move back down, and move down, and then move up again. It will have moved through 4 amplitudes in that time, okay? Delta S is going to be equal to 4 times x naught. So the average speed of this guy, of the particle, is 4 times x naught divided by capital T here. All right? That's the first thing we want. Now let's look at the actual speed of the wave. Okay? Again, V is equal to delta S over delta T. In this case, if we consider delta T the period again, right? Delta S as the wave moves forward. Once it moves through time of 1 period, it's going to have moved 1 wavelength. Okay? So what we end up with is lambda divided by the period. And something really useful here is that the frequency, remember, of this wave, all right, is 1 all over the period. This is true for any object. So what we actually end up with here for our wave function, our wave equation, excuse me, is that the wave speed is equal to the wavelength times the frequency. And that is going to be our equation that we're going to be using all this year. All right? So that is incredibly important towards analyzing waves. Okay? Really quickly, all right, what is the control variable for all waves in a single medium? Well, it is wave speed. Okay? Wave speed, as you see in the notes, depends on the properties of the medium, okay? Not how fast the medium vibrates. Okay? Okay? So if you want to change the wave speed, you got to change the medium. Right? So in one medium, you have constant wave speed. So any wave that you generate, okay, whatever the frequency, it'll move forward at the same speed. It'll just be the wavelength that changes. So the next question is, what is the control variable when a single wave crosses the boundary between two media? So we change media, okay? So we have a new wave speed, all right? Frequency is what stays constant. The reason for that, frequency only depends on the source generating the sound, or generating the wave. Okay? So this is true for both light and sound. Okay? The frequency, all right, is going to stay the same. All right. Okay, so waves in 2 dimensions here. All right. Oh, actually, sorry. Right below there, one more thing that you have is the electromagnetic spectrum. Okay. These are all the frequencies and energy levels at which we see light, which is a transverse electromagnetic wave. All right. So you have your own little electromagnetic spectrum there. The 7 major regions that you need to know: radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, as well as visible light. And in there is the wavelengths of each. Okay, the ranges of the wavelengths. All right. And we will be studying this more throughout the year, needing to know the frequencies as well as the energy levels of these guys and the wavelengths of certain types of radiation.